Hello viewers, welcome back to my channel. So today we are going to discuss on efficiency of DC motors. So in the previous video we have discussed that there are a certain number of losses in DC motors, and we have gone through it. So now we have understood that none of the DC motor is 100% efficient because of the types of losses that are present, which we have discussed. So it is important for us to know what is the efficiency for a given machine for a given output and for a given value of losses, because it is important for us to run a motor always near the maximum efficient point. So to understand this particular mathematical derivation, we are considering following parameters. So first one is the term RAT. So this term refers or represents the total resistance of the armature circuit. So now the armature resistance is given by the term R suffix A. Now if there is a series field present, if it is a DC series motor, then series field will be in series with the armature resistance. So that is denoted by RSC, and interpole windings and compensatory windings, these two windings are in series with the armature circuit. So its resistance is denoted by Ri and Rc, and also the brushes which are necessary to supply the electricity to the armature, it is made of carbon, so it will also have certain resistance, and this will also come in the armature circuit. So all these resistances combined together is represented by a single value of resistance called as RAT. Okay, so this is the total resistance of the armature circuit. So understand this parameter. Next, so I stands for the input current or the supply current. So this is the current which is drawn from the supply, and this will power the entire DC motor including field and armature, and also it has to compensate the losses. So ISH is the current through the shunt field. So we have seen this representation earlier also. IA is the armature current. So if at all there is a shunt field present, then main current minus the shunt field current will be the value of the armature current. So we have seen this expression while discussing the types of DC motors. So let V be the supply voltage. So that is the notation we are using. So with the following parameters, we shall see the derivation of the efficiency equation. So now the total copper loss in the armature circuit or total electrical losses in the armature circuit is I square R losses, and R is the effective resistance now. Okay, so effective resistance of the armature circuit, which is given by the term RAT. So this I square R, and in the armature circuit the current flowing is armature current, so IA, and effective value of the resistance what we have used is RAT. So I square R losses here is given by IA square RAT. Next, losses in the shunt field. So supply voltage into current, so will give us the power loss. If we know the value of the shunt field resistance, then we can go for ISH square RSH. Both are fine, but for the time being we are not aware of the resistance of the shunt field, so we know what is the supply and we can measure what is the current through the shunt field winding. So this particular representation is easier for us. So mechanical losses is given by frictional losses plus windage losses. So for the time being, we are not using any representation for these losses because these are mechanical parameters and we do not have any electrical equivalent parameters to represent these losses. Okay, so we will have to use mechanical terminologies which we are avoiding for the time being. So let us try to make all the things electrical first, or the electrical equivalent. Next, core losses. So core loss is eddy current plus. In types of losses, that how we are going to consider this type of losses, because it is not so easy to measure this. Next, stray loss. So stray loss is usually taken as mechanical loss plus core loss. So what are these unmeasurable losses we call? So we, for a larger machine, we consider stray loss as 1% of the total output power. So it is given by mechanical losses plus core loss. So now the total losses which are present will be the armature copper loss, field loss, mechanical loss and core loss together added, called as stray losses. So the constant loss is given by the formula shunt field loss plus stray loss, and here we know that stray loss is mechanical loss plus core loss added with the shunt field loss. So these losses are called as constant losses. Let us denote it by the term Pk. So P stands for power and K stands for constant. Okay, so we are denoting it by a representation P suffix K, which corresponds to constant losses. So now constant loss plus variable loss is the total loss in the machine or the motor. So total losses is variable losses plus constant losses. So for the timing, I will not call this as a copper loss. I will call it as a variable loss, because if I want to call it as a copper loss, then it should be in the copper only. But we have a brush resistance added here, and brush is not made of copper, it is made of carbon. So I will use the term variable losses and constant losses. Okay. So efficiency, general expression for efficiency is output divided by input. Okay, so now electric motor is a device which converts electrical energy to mechanical energy. For the time being, we don't know what is the mechanical output of the motor. So we know what is the total losses. We also know what is the value of the input. So if we subtract losses from the input, we will get the output. So here is the expression. The efficiency is given by output divided by input, and output is mechanical. So we want purely electrical terminologies here, which we are aware. Because for the timing, let us not complicate the topic by introducing mechanical terminologies. Okay. So using the electrical equivalent terminologies, this output can be obtained from input minus losses. So these are the electrical parameters. Also our input is the electrical parameter, which will be easier for us to understand. So input is given by V into I, because I is the input current, V is the supply voltage, minus losses. So losses are constant losses and variable losses. Okay, so here we have total losses. So subtract this. So minus within the brackets. So we are expanded and written this divided by input. Okay, so let us rearrange this equation. Let us separate out the denominator for each term. Okay, so now here we are having the terminology efficiency is given by Vi minus Ia square R AT minus Pk divided by Vi. So I want a small comparison here. Now this field current is very small compared to Ia. Okay, so if it is very small compared to Ia, then I can say that Ia is nothing but equal to the line current. So if the field current is very small, this is in case of the larger motors, where the armature current will be some 20 amperes and field current will be 0.3 amperes. So compared to 20 amperes, 0.3 is very small value. So, and in larger machines, this will be much smaller. So the value of Ia will be almost equal to the line current I. So considering this assumption, what we get is the efficiency of the motor, wherever there was Ia in the previous equation, we have replaced it by I. So this term Ia square is now I square. So now let us separate out the terms by dividing throughout with the denominator. So we get this vi by vi is 1, and is square by vi we get I, and pk by vi. So this is the equation which gives us the efficiency of the motor, and in this particular equation we can observe that the efficiency depends on the line current, and line current increases with the load. So as the load varies, the efficiency will also vary. Now we have seen the efficiency curve for various electrical machines, maybe transformer or DC generator, whatever it is. And if we plot efficiency versus load, then the shape of the curve, what we usually get is like this. So efficiency will increase with the load, and at one point it will be maximum, and then it will once again decrease with the load. So now we have to find out what is the maximum value of this efficiency. So now if this is the equation for efficiency, from this equation without having a curve, mathematically how to determine the maximum value. So now this is a function, efficiency is a function of current. Okay, so I'm taking efficiency here in the y-axis, and load current or the line current in the x-axis. So this will be something like y is equal to a function of x. So y is equal to f of x. So considering this, if we have a equation which has two variables, then considering this shape of this curve, if we find out the slope at each and every point, when the efficiency is maximum, the slope will be 0. Okay, so when the efficiency is maximum, that is at this point, the value of the slope will be 0, and for this slope to be 0, that we have to find out, and we know that slope is nothing but dy by dx. Okay, if we differentiate the given function fy is equal to f of x with respect to x, then we get its slope dy by dx, and that should be 0. So here y is efficiency and I is current. So to find out the maximum efficiency, what we have to do is we have to differentiate this term with respect to I. So this RHS will be differentiated, and we are equating it to 0 to find out the value of I where efficiency is maximum. Okay, so d by di of this term, okay, d by di of this term we are taking now, and we have to differentiate. So let us apply the mathematics and differentiation rules. Okay, so quickly start differentiating this equation with respect to I. It should not be difficult because this is a constant, and there is a constant multiplied by a equation, and this one is in the denominator. Okay, so the differentiation is constant, differentiation will be 0, and the differentiation of this term I square we had, so it became I. So now what we get is this I goes actually, so RAT by we will have to remain, because the differentiation of this term, and the differentiation of this is I square. Okay, so if we rearrange the equation, we arrive at the this equality, that is the constant loss should be equal to variable loss. So this is true for any electrical machine. If we consider, if the constant loss is equal to variable losses, then the efficiency is maximum. So now at the maximum efficiency, what is the value of current? Okay, so because we have to know what is the value of x and what is the value of y. So if we take pk is equal to I square RAT, we get the maximum value of the efficiency. For that maximum value of efficiency, what is the value of I? Okay, because at what value of current this pk will be equal to I square RAT, so that we can get maximum efficiency. Okay, so this is given by the expression. So the current I square here, I have taken it as Im square just to identify it as a current corresponding to maximum efficiency. Please do not get confused. This is not the maximum current. This is the current corresponding to maximum efficiency. So Im square will be equal to Pk by RAT. Let me multiply and divide it by the full load current square. Okay, just for my convenience. So if I rearrange this equation, then the maximum efficiency is obtained at this value of current, which is a fraction of full load current, which is given by root of Pk by IFL square. So constant loss divided by full load variable loss, take the root of it, multiply it by the full load current, that is the value of current at which the efficiency will be maximum, and Im is always less than IFL. So I hope this derivation is clear to everyone. It is a very important one, efficiency and the maximum efficiency. So please do not forget to subscribe to our channel and hit the bell icon. Also you can subscribe to our sister channel, which is Sahadhyayanam, for different for today. Thank you.